Today we're going to talk about proof by cases. When we talk about proof by cases, sometimes we're given a result, and the result involves some set of elements. And when we look at the set of elements, they have something in common that they're all members of that set, but then they might have some characteristics that make them distinctly different than other members of the set. And this makes completing a proof difficult with just a generic member of the set. So what we do is we look at the members of the set and we say, well, these have this characteristic and these other ones have this other characteristic, and maybe this third group has this characteristic, and we group them by the characteristics that we can actually follow through with our proof and use a generic element from each with the different characteristics they might have. Now, it's a long definition. It's kind of a complicated hand-wavy thing. An example might help. So sometimes we're asked to prove something about the integers. Now, one of the common characteristics of the integers that we know how to work with is whether the integers are even or if they're odd. So we can actually break the proof of a result about the integers into two cases. So we can have a case where the integer is even and a case where the integer is odd. And then we can use the definitions of even and odd to help us in our proof. So here's an example of that. We have n as an integer, and we say if it's an integer, then n squared plus 3n plus 5 is an odd integer. Now we need to show this for all integers, but knowing just that n is an integer, I can't do anything with even and odd from that. So instead, I'm going to break it into two cases. The first case will be when n is even, and the second will be when n is odd. So given that n is an even integer, now I can write n equals 2 times x for some integer x. And I can substitute in 2x everywhere there's an n in my n squared plus 3n plus 5 expression. When I do that, I end up with 2 times 2x squared plus 3x plus 2, which is an integer, plus 1. So I have the result that I was desiring. However, I've only shown that this is true when n is an even integer. So now I need to consider a second case where n is odd. So now n is an odd integer, so I'm going to write it as 2y plus 1 for some y that's an integer. And I'm going to do the substitution of 2y plus 1 in for every n in the expression n squared plus 3n plus 5. And when I simplify that down, I find that, in fact, n squared plus 3n plus 5 is equal to 2 times 2y squared plus 5y plus 4, which is an integer, plus 1. So I find my result that n squared plus 3n plus 5 is odd by definition. Now, this example is the example that we went with for a reason. One of the most common proof by cases that we're going to run into for now is going to be dealing with even and odd. So one of the things that comes up with even and odd is this idea of parity. We use the word parity. The parity of a number is whether it's even or odd. So we say they're the same parity if they're both even or both odd, and we say they're opposite parity if one of them is even and the other is odd. So we actually have a result about parity that is more important than a result because we're going to keep on using this over and over again. So we're going to call it a theorem. We have x and y are integers. Then we have the statement that x and y are of the same parity if and only if x plus y is even. So this is a biconditional. The proof is going to require two different directions. So the first one, we're going to assume that x and y are of the same parity and show that x plus y must be even. Now, them being the same parity means they're both even or both odd. So we're going to have two cases to consider. We're going to have x and y are both even and x and y are both odd. So we do that, we use the definitions, and we come to the conclusion that x plus y is even. So please take the time to look through the details of that proof and make sure that they make sense. Once we've completed this proof, then we need to prove the converse. We need to prove that if x plus y is even, then x and y are of the same parity. So to do that, we're actually going to use the contrapositive. So we're going to assume that x and y are of opposite parity. And we're going to show then that x plus y is odd. So we're doing the not Q implies not P option. All right. So we have two cases. One of them is x is even and y is odd, and the other one is y is even and x is odd. Now, we've worked through the details of the first case. Again, this is plugging in by definition and doing some arithmetic and coming to the conclusion that x plus y is odd. And then we don't even bother writing the proof of the second case because it doesn't change anything to change which one's x and which one's y. You might have noticed in the last proof that we didn't write out the proof of the second case. Now, a common phrase that we use is without loss of generality. Sometimes this allows us to not need to do both cases for proof to be done. So in the previous proof, I could have said without loss of generality, let x be odd and let y be even. And that indicates that it's still general, like I could switch the x and y, it's fine, nothing changes, right? So we use this, and sometimes we abbreviate it with a WLOG, sometimes WOLOG. And when you see this, basically what they're saying is there's nothing different. Like it's really just changing some letters. It's still general enough, right? So here's an example. I have a and b are integers, then a, b is even if and only if a is even or b is even. Now this is again a biconditional result, and it's one that's important enough that we're calling it a theorem. So we're going to first assume that a is even or b is even. Without loss of generality, we can choose one of them to be even. So let's say a is even. That without loss of generality tells us that it doesn't matter if it's A or B that's even, the result's going to work out the same. So we're going to work, though, under the condition that A is even. So using the definition of even with respect to A, then we can rewrite A times B, and we can see that A times B is in fact even by definition. Now, we need to show the converse as well. The converse says if AB is even, then A is even or B is even. This is another case where the direct proof of the converse is maybe not the easiest thing. So we're going to instead look at it and show the contrapositive of that statement. So we're going to assume that A is odd and B is odd. So that's our not Q statement. So by definition, I have A and B rewritten as odd integers. And I can do some arithmetic then, and I find that AB is in fact odd. So this theorem is proven.